Welcome back. This is the second lecture for this course of radio astronomy. In the first lecture, we introduced the field of radio astronomy, why we are so passionate and so excited to do radio astronomy in today's world. What are the futures even for radio astronomy in India? We also showed lots of motivation in different branches as radio astronomy plays a very important role in the overall astronomical findings. So that was the first lecture. In this lecture, what we plan to do is step a bit back and review some basic electromagnetic theory which is essential to go ahead. As you understand, we are talking about radio astronomy, means radio signals which are getting received by the telescope emanated from cosmic sources distance away. Now, of course, it involves electromagnetic wave propagation. It involves certain electromagnetic wave dispersion, reflection, refraction, several other things. It is governed by the basic Maxwell's equation. All those we have learned mostly as an undergraduate. Now, we could have skipped this portion and gone ahead and just assume that you know, but people come from different backgrounds and have different retention of what they have done in the undergraduate. So we thought as a completeness, it's better to spend one lecture in reviewing certain basics. We will not go in details. This will also follow up with a tutorial which will cover some solving numerical examples, and that will also revise your already learned concepts a bit more, which will help us to go forward in this course. So with that, let's go and start reviewing the electromagnetics. The basic classic electromagnetic books are by J.D. Jackson, but my favorite is the last one, Electromagnetic by D.J. Griffiths, which is more than sufficient for most of the purposes to do. Okay, so with that, we just and of course the antenna theory. We will also come separately in week number 3 and discuss more. Starting with Maxwell's equation. Now, it's very important. We will not go into details the historical development of all these equations, but they're fascinating nevertheless. So there are 4 equations. Del dot D is equal to rho, the charge density. D is the displacement current linked with electric field. Del dot B, the magnetic field B, is equal to 0. Del cross H, or curl of H, magnetic field intensity, linked with magnetic field, is equal to J, the current density, and curl of E is equal to minus del B del T, where B is the magnetic field. So, if you perform del dot J is equal to 0, and from there, the continuity equation also gives you del dot J plus del rho del T is equal to 0. Now, if you club both of them, you can definitely write the del dot J plus del D del T is equal to 0. Okay, so that's very nice. So we have now then the modified equations as del dot D equal to rho, which are already there, del dot B equal to 0, del cross H is equal to this current density plus del D del T, and the final equation curl of E is represented by this partial derivative with the time of the magnetic field. Now these sets of equations are also called Maxwell's equation. In fact, the first one you can relate to the Gauss's law. The second one is non-existence of magnetic monopole. The third equation is the modified Ampere's law, satisfying conservation of charge. And the fourth equation is the Faraday's laws of induction. Now, if we consider Maxwell's equation in free space, it refers to like vacuum where no dielectric and magnetic media is present. So epsilon and mu are all equal to 0, dielectric constant and permittivity. No charge density and no current density, so rho and J are also equal to 0, and no means of conduction. That reduces the Maxwell's equation to del dot E to be equal to 0, del dot B was already 0, and curl of E is minus del B del T, and curl of B is mu 0 epsilon 0 del E del T. These are the Maxwell's equation in free space. Now let us take a look and revise a little bit more about Poynting's theorem. What is Poynting's theorem and what is Poynting vector? The conservation of energy in an electromagnetic field is often referred to as Poynting theorem. So there is charge Q subjected to an electromagnetic field of E and B. The Lorentz force which acts on that charge is given by F is equal to Q, the charge times electric field plus the cross product of velocity and B. This is very well known. So that is the Lorentz force. Now, if that from there we want to equate what is the mechanical work done by the fields on the charge Q, then that rate of change of energy is equal to F dot V or QE dot V. Okay. The magnetic field does no work. We can easily generalize the above equation to an arbitrary distribution of charge density rho using the fact that J is equal to rho V. Then the above equation takes the shape of the rate of change of this mechanical energy is equal to the integral of J dot E, volume integral of J dot E. Okay. So by using Maxwell's equation, again you can write it in terms of the curl of H. So you replace that and then use the vector algebra form that curl of H dot E is equal to the right hand side, and if you replace that, finally you take this shape of the expression. Okay. If now you assume that the medium is linear and isotropic, then the displacement current becomes just a scaling of the electric field, and same as the magnetic field and intensity. And if you do that, then finally you manage to get the electromagnetic energy in terms of E, D, B, and H. Okay. And then you also have, putting into the expression, you have J dot E, the volume integral of that is equal to volume integral of, replace that J dot E with this del U del T plus divergence of cross product of E cross H. Sorry. Since the volume integration V is completely arbitrary, we can write this last equation as a continuity equation, and that one in the box is now called the Poynting's theorem, or follows the law of conservation of energy. Okay. Now, what is a Poynting vector? Defining Poynting theorem, now we come to Poynting vector or Poynting flux, is defined as this vector S, which is nothing but the cross product of E and H. Okay, and it is a measure of the rate of energy flow per unit area at that point. Relationship between a vector and a scalar product. You know that the vector product, vector potential is defined as A, where del cross A, curl of A, gives you the magnetic field. So if you replace B in the Faraday's law, in the Maxwell's equations, you get this del cross E plus del B del T as del cross E plus del A del T equal to 0. Hence, you arrive at the relationship of E is equal to minus gradient of phi, where phi is the scalar potential, and minus del A del T, where A is the vector potential. Very good. By using Faraday's law from Maxwell's equation, we get, if you just follow this expression, we will be sharing the slides, and then by setting C is equal to square root of 1 over square root of mu 0 epsilon 0, you finally derive this huge expression. Then eventually, if you use the Gauss's law from Maxwell's equation instead of Faraday's law, you finally get to another set of expression of del square phi plus derivative to T of divergence of A is equal to minus rho over epsilon 0. These are all the basic electromagnetic theory, and so that's what relates the phi and the A if you replace the basic identities in the Maxwellian equation. So far what we have done is we have reviewed a little bit of Maxwell's equation in different form. You can keep replacing one with the other. Remember, things do change, the expressions do change. Mostly in the radio astronomy, we'll be using free space equations, but sometimes things do pass, radio waves do pass through lossy medium, like ionosphere, and things changes. But mostly it will come when we discuss the different wave propagation properties, and also during the antenna radiation pattern study. The antenna is a very vital thing for radio astronomy. That is the basic core behind creating a radio telescope. So we need to understand more how the antenna radiates, what are the antenna's far field radiation pattern, etc. So some of those cases we will see use of very genuine use of tricks of replacing A with B and different identities, and so getting a primer in the electromagnetics is essential so that you can follow those. Otherwise, those steps won't be easy to follow. So far we have just finished the Maxwell's equation. I have introduced Poynting's theorem and the Poynting vector. So next is wave equation. So wave equation is very well known. You have double derivative with respect to x, the space vectors on one side, linked with 1 over the v squared, the wave velocity, times the double derivative to time on the other side. So we have then the function which is to be solved is a function of both x and t. So we kind of separation of variables. We assume that there are two different functions, one just spatially related and function of space, and one function of time. So then if you do that, you get two separate two sets, a set of equation, one with respect to time and one with respect to space. If you keep solving that, by just following this simple solutions, assuming, then finally we arrive at, by doing the standard separation of variable technique, we finally arrive at the x, the spatial component, being nothing but superposition of sine and cosine function with two constants a's and b's and two more constants parameters small a and small b. Similarly, the other one, the time variable, also will come with few more constants and basically one cosine function and one sine function. They are both harmonic functions. Okay, so ultimately the u can be written as a cosine function of time and a sine function of x, and that's the final solution to the